Okay, go to the slide that says instantaneous rate up top. Okay. This is going to be a little piece of information that those of you who take calculus are already kind of familiar with. How many of y'all are enrolled in calculus right now? Okay, so you've talked about instantaneous rates. What's another way for finding a tangent to a curve? It's called the derivative. So you don't have to know calculus to do this, but ultimately, if on the AP you're asked to find the instantaneous rate at any particular given time, given the curve of concentration versus time like this, because we know that as time proceeds, the concentration of reactants, we always are looking at reactants. We don't very much look at product production and kinetics. The concentration of the reactants decreases as time goes by. So if I were to say, what's the instantaneous rate 8 minutes after the reaction starts, you find the 8-minute point on the curve, and then you draw the line tangent to that curve. The slope of that line is the rate. Why does slope equal to rate? Well, what is a slope? I'm talking about just math. Change in what over what? Y over x, right? Well, and it's actually not a change in x, right? Because we're at a certain time. We're at one point of time. So what is y? It is concentration. So if we're looking at a change in y, well, any general slope is a change in x. Concentration over change in time. Isn't that what rate is? Change in concentration over change in time? All right. So that's all you do. You find if you on the AP actually want to take the derivative, go for it. They're going to go ahead and they accept it. I've seen questions where there's been some calculus that I don't even remember how to do that I had to hand off to some professor who remembered calculus. So you can use calculus if you want. At minimum, draw the tangent to the curve. You all remember how to find the slope of a line, right? Right? Okay, that's all you need to do. Okay, now let's get into the big stuff for the day. And that is our third way to determine what the rate of a reaction is. So our first way was use of mechanisms. Our second way was using the method of initial rates. And the third way is using integrated rate laws. Some good old P chemist that loves calculus decided just to integrate these particular reactions and see what happens. So if you have this, do we all agree that that's the rate law for a zero order reaction? You're comfortable with that assumption? Okay. Well, if I were to integrate this from time 0 to time t, which you don't have to know how to do, I would get the following equation. Not rate. It's going to be one of those days, guys. Concentration of A minus concentration of A naught is equal to negative KT. What does this mean? Well, this equation is very useful. This is the integrated rate law of a zero order reaction because I can look at a reaction knowing that A naught is the original concentration, A is the final concentration at time t, or when that time t passes. I could ask a question, after 10 minutes, if my original concentration of a reactant is 5 molar, how much would be left? Okay, you can use it to plug and chug to find time, you can use it to find K, all sorts of things. You will have to memorize this particular one. There's only 2 equations you're going to have to memorize. This is one of them because this is not on the AP equation sheet. All right, so you have to memorize the integrated rate law for a zero order reaction. I smell orange. That's okay, it doesn't bother me, I just smell it. All right, so I'm going to show you in some word problems after I go through zero, first, and second order how we would apply this. But another thing you have to know is how to graph it. You're going to get some data where you're going to have to graph 3 different ways and determine if it's a zero, a first, or a second order reaction. And I'm going to show you how to do that quickly in your calculators. But to prove something is a zero order reaction, what chemists love to do is to linearize things. We've done Clausius-Clapeyron. We're going to do the Arrhenius equation tomorrow, where we like to make things linear so the slopes are meaningful. Looking at these variables here, which one of these is constant? A original, right? So I'm going to take that and I'm going to move it over to the other side of the equation. And I'm going to get negative KT plus the concentration of A naught If you look closely, y equals mx and b. That's our linearization of the zero integrated rate law. So if I wanted to graph something to prove it was a zero order reaction, I would put time on the x-axis and concentration of A on the y. Okay? This one's going to have a negative slope. So if I were to ask you, what's the K? What's the rate constant of this? If I gave you data and you found out it was a zero order by graphing it this way, how would you find the rate constant? The slope. You cannot have a negative K. So the absolute value of the slope, for any order, the absolute value of the slope is going to be your K. You do need to learn this as well, the three ways of graphing. And I have a little trick to memorizing the three ways of graphing that I'll show you as soon as I get through all of these. Okay? All right. I know it sounds like a lot to learn, but it's not that bad. Just hang with me. Now, still talking about zero order reactions, there's something called half-life equations. I'm going to derive them. You don't need to derive them. You really don't even need to memorize this one particularly. I just want you to understand what a half-life is. Everyone thinks half-lives has to do just with nuclear decay, and it doesn't. Every reaction has a half-life. So what is a half-life? The amount of time it takes for half of the reactant to turn to product, right? So let's go ahead and take the zero integrated rate law. Concentration of A, uh-oh, it's doing that weird thing again, minus, goodness gracious, minus A naught is equal to negative KT. I did something last time. I think by changing pages and going back, it helped. So, okay, let me pause it. Maybe it'll, that was a nice pause. All right, let's try it again. A, nope, minus A naught equals negative KT. All right, so if I wanted to make this a half-life equation, what do I know about the original amount compared to the final amount if it were dealing with one half-life? It would be half. So anywhere it says A, I'm going to plug in half of the original. Then it's working again. This is just so wacky. Okay, so does that make sense to you? So I'm going to plug into A naught over 2. So A naught over 2 minus A naught is equal to negative K. But right when I did that, I'm going to say T1 half because that's equal to a half-life. So I'm going to make this a half-life equation and isolate that T1 half. But before I can do that, I got to simplify this on the left side. This is also 2 over 2, right? So what is this left side actually? Negative A naught over 2, right, is equal to negative K T1 half. And if I want to do a half-life equation and divide each side by negative K, A naught over 2K is equal to T1 half. So that's my zero order half-life equation. Do not memorize this one. No memorization. Do not memorize. Because we can get around memorizing this one, and I'll show you some ways, but it's important for me to show you this example because I want to make a point when it comes to first order when we get there, because right now we're doing zero order. Okay? Does everyone understand kind of where I got it? In lieu of memorizing it, what you can do, if they say, oh, the original concentration of this particular reactant is 50, what's the half-life if K is this? What would you do? Plug in 50 and then plug in 25 and then solve for the half-life. So there's a way around memorizing this particular equation, so don't freak out about it, okay? Let's go on then and talk about first order. And again, I'm sure you're like, what does any of this have to do with anything? Just hang with me. We'll get to the important stuff once I've gone through everything. So here we have a integrated rate law for a first order. To get that, they integrated a first order rate law to get the following. ln of A minus ln of A naught is equal to negative KT. So again, this is going to have a negative slope if we were to graph it. Which one of those things on the left are actually constant? ln of A naught. So I'm going to pull that one over again. And in doing so, I've linearized my equation. And if I wanted to graph a first order and prove that something was first order, what would I put on the x-axis? Time, good. And then on the y? Nope. Natural log of concentration of A. If I get a better line with this one than doing just concentration versus time, I have a first order reaction. What do I mean by better line? Does anybody remember? My R is closer to 1, correlation coefficient. We'll talk about that when we do the problem. It's called the best. We're going to draw the best fit line with our data, and the one that has the best R, closest to 1, is going to be the correct possibility. Okay? And again, if I ask you for the slope, it's going to be, the K, it's going to be the absolute value of that slope. Got it? And the y-intercept is equal to the natural log of the original concentration. So even if I were throwing a problem asking me what the original concentration was, I can do that by e to the y-intercept and get the original concentration. All right? Maybe. Y'all look so excited. You'll be excited. It'll be fun when we start using the calculator, I promise. So, first order reactions are super, super duper important when it comes to half-life. Does anyone know why? All nuclear reactions are first order. When we talk about beta decay, alpha decay, all of that, these are all first order reactions. So I do expect you to memorize the half-life equation here. Oh, I didn't mention back here, this is on the AP sheet, so you don't need to memorize it. Just be careful because it's not labeled as first order. First order and then second order are listed, but it doesn't tell you which one is which, so you do need to know that the natural log is the first order, okay? Don't memorize it though. However, the reason I need you to memorize this half-life equation we're going to derive is because it often shows up in the multiple choice. It's hugely important. There's a whole area of science called nuclear chemistry that depends on this first order reaction. When we get to doing nuclear with organic as the very last unit, we totally revisit first order kinetics. So again, our ln of A, our first order integrated rate law equals negative kT. If I were to make this a half-life, I take ln of A and replace it with what? Half of the original, A naught over 2 minus ln of A naught is equal to negative K, and I put a little half here because that's half-life. Now, how can I simplify mathematically natural logs? Subtracting that division, right? When we subtract natural logs, it's actually division. So I'm really doing ln of A naught over 2 divided by A naught is equal to negative K T1 half. Well, this can be simplified even more to be what? Ln of 1 half, okay, is equal to negative K T1 half. Can someone find that for me? What is ln of 1 half? Well, I know it. It's negative 0.693. If you take your calculator, put natural log of 0.5, you get negative 0.693 is equal to negative K T1 half. And if I want to isolate, I divide by negative K. So my final integrated rate law, not integrated rate law, half-life equation for a first order is 0.693 over K. You need to know this. Now you can stay where you are, but I'm going to kind of flip back to the other half-life equation. Take a look at this one really closely, right? Now look back at the other half-life equation. Does anyone see something different about the equation? Something more than, has nothing to do with decays. The other one does not have A naught in it like the zero order. So what does that mean? That means a first order's reaction, its half-life is independent of the original concentration. Anyone see the importance of that? Aren't all radioactive things, don't we say that the half-life is set like uranium has a certain half-life, or carbon-14 has a certain, it's a set. Regardless of how much you start with, these things have a set half-life. Okay, and this proves that. Versus these other reactions, if we change in this equation the amount we start with, we're changing the half-life. So that's a really, really important part about a first-order reaction. Half-life is totally independent of the original concentration. So half-life independent of the original concentration. Okay, so let's go on now and move to second order. For a second order reaction, if I were to integrate that from time 0 to time t, I would get the following integrated rate law. 1 over a minus 1 over a naught. This time we get a positive kt. Again, this is on the AP sheet. You do not need to memorize it. However, you do need to know how to graph it. So if we were going to graph, what would we put on the x? Oh, let me go ahead and linearize it first, I guess. So I get 1 over a is equal to kt plus 1 over a naught. So now y equals mx and b. If I were to plot, what would I put on the x-axis? Time. And then on the y? Reciprocal. All right, and then k is equal to the absolute value of the slope. And I know the slope's positive here, so it wouldn't matter, but knowing the slope is positive is actually going to help you recognize questions. Sometimes they'll just give you axes with lines, and they'll say, is that a first, second, or 0 order? And you're like, oh, the slope's positive, so that must be, so it'll be a clue for you to answer certain questions on the AP. All right, so do not memorize. And the last half-life equation, again, you don't have to memorize this one, only the first order one, but I always like to derive where things come from. So, because all 3 of these are in your textbook along with all their half-life equations. So we're in the reciprocal. 1 over a minus 1 over a naught is equal to positive kt. I'm going to plug in 1 over a naught over 2, right? Minus 1 over a naught equals kt 1/2. That I can simplify to 2 over a naught minus 1 over a naught equals kt 1/2. 2 minus 1, I get 1 over a naught is equal to k t 1/2. Divide by k. 1 over a naught k is equal to the half-life. But again, we're going to get around where you don't have to memorize these. But I think it's really important you see where things come from. Okay? So the synopsis of all 3 are given to you in the next 3 pages. That's just everything you've already seen. Okay? 0, first, and second. Numbers 9 through 12 we're going to work and just use the integrated or half-life equations depending on what we see fit. So I need you to have your calculators out. These are just plug-and-chug math problems. And then we'll get into some graphing. So number 9 says, the decomposition of H2O2 and water and oxygen follow first-order kinetics with a rate constant at a certain particular temperature. They want to know the concentration after 10 minutes if the original is 0.2. Well, the trick here is reading the problem. It says first order. So you know it's this weird thing with time and original concentration. You need to think to yourself, that is an integrated rate law problem. So I'm going to go to my AP equation sheet because first order is on there, and I'm going to see it says ln of A minus ln of A naught equals negative kt. All right, I am solving for H2O2 after 10 minutes, so I'm solving for that. Do I have my original concentration? Yep, it's 0.2. Do I have my K? Yep, it's 0.0410. Units are crucial per minute. Okay, and then how many minutes do they want it to run? 10 minutes. You need to make sure these units match up. If they gave it to you in seconds or something, you need to convert it to match that K. Make sure they're the same unit. So don't forget to do the ante after you're done, but what is that concentration? of H2O2 after 10 minutes. Should it be less than or more than the original 0.2? Less, right? We start with a certain amount. It should go away as the reaction progresses. 0.133, 0.133 molar. Okay, and that makes sense to me because it's less than 0.2. Someone in the previous class got a negative answer, so that right off, you can't have a negative concentration. So there are tricks, ways to tell if you're on the right track. So let's go to the next one. It says the decomposition of N2O2 to O2 and NO2 follows first order kinetics again. If a sample has an initial concentration of 125 E negative 3 and falls to 102 in 100 minutes, calculate the rate constant. Whenever you find rate constant, I always want you to include units. Knowing that trick is going to help a lot in these problems. So first order kinetics, we know that's natural log of A minus ln of A naught equals negative KT. So do I have A? Yeah, it falls to 1.02 times 10 to the negative third. Do I have A naught? Yeah, it's ln of, and I forgot to put ln of here, ln of that, ln of 1.25 times 10 to the negative third equals, solving for K, and then time is 100 minutes. So go ahead and solve. So we got 0.00203 as an answer, but we need some units. So let's talk about our trick. This was overall a first order. The trick was 1 over, what was our unit of time? Minutes. What's 1 less than the overall order? 0. So m to the 0. We don't even put it in there. I love the trick. The trick is awesome. Questions? No, they're just, it has to happen at the same temperature throughout, okay? K's are temperature dependent, and they're only good at a particular temperature. So if you were to repeat this experiment at another temperature, the K would be different, okay? And you're going to see that in the Arrhenius equation, that K's go up as temperature goes up, okay? All right, next one. In problem 9, how long would it take for half the H2O2 to decompose? Well, let me pop back to 9 and get some data. 9, I had the K of 0.0410 and my original concentration of 0.2, 0.0410. So they gave me a K of 0.0410 per minute and an original concentration of what? 0.2. Now, if I want to know how long it would take half for it to decompose, what's that also known as? Half-life. You can do one of two things. You could take the integrated rate law for first order, plug in 0.2 and plug in 0.1, and plug in K. But this is really helpful knowing this it's doing it again. Knowing this half-life equation. Yikes. Let me try to pause it again and maybe undo it. It kind of worked last time. So T1/2 is equal to 0.693 over K, remember? 693 over K. So all I need to do is plug in my K. And what am I going to get? A time in what unit? In minutes. So plug in 0.0410 in there for me and tell me what you get for minutes. Just 3 sig figs. Tell me one more time. 16.9. I know I haven't been the big sig fig crazy lady lately. However, some of you on that last exam were going nuts. Like there were people with 7 sig figs and answers. Y'all are reverting to physics. Be realistic. 2, 3, or 4 sig figs, period, in all your answers, all right? Don't go crazy. If you're crunched for time, I don't have time to worry about it. So any questions on this one? Do you see why it's easier just to use that? But you all understand you could have used just the regular integrated rate law, put in 0.2 and 0.1 and solved that way as well. Okay. All right, let's go on to 12. This is second order. Woohoo! with a rate constant of 0.048 and they give us an initial concentration of 0.4, we want to know what the concentration is after 15 minutes. So who remembers what the second order rate law, integrated rate law was? 1 over, good, 1 over A minus 1 over A naught is equal to positive KT. And again, that's on your AP equation sheet. You go find it and you just plug and chug. We want the concentration after 15 minutes. So this is our NOCl after. Our NOCl before initially was 0.4. Our K, did they give it to us? Yes. 0.048, 1 over second molarity. Does those units make sense? Yeah, it sure does. Second order, right? So the m is to the first, which is 1 less than 2. Okay. And then time is what we're looking for. Oh, no, we got to put time in. Do you see a problem, though? What are they giving us the time in? Why is that a problem? Look at that rate constant. So I'm going to go ahead and right here and just write a conversion for every 1 minute. I have 60 seconds. All right, solve away. So we got a final answer of 0.0219, which totally makes sense because it's less than the original 0.4 concentration. One more and then we'll go on to the fun part. Graphing's my favorite. If the initial concentration of NOCl above is described as 0.4, calculate the half-life for the decomposition of this reaction. Well, here's the deal on this one. I don't want you to memorize that second order half-life, so let's just use the actual second order integrated rate law. 1A minus A naught is equal to KT. Well, they want to know the time, the half-life, and if the original is 0.4, that's what we'd put here in the original. What would we put here? Good, 0.2. And then our K from the other page was 0.048. Was it seconds? It was seconds, right? And we're going to find our time. And our time based on this K is going to come out in seconds. Leave it in seconds. That's another thing I noticed on the AP. On that Clausius-Clapeyron one, a lot of you would solve it and then all of a sudden just randomly to put it in atmospheres. Don't change units unless you are asked to, because that could lead to you making an additional mistake. So why would you want to do that? Can I get a second on that? 52.1? 52.1. Seconds. Okay, I'm glad we're done writing for a minute because this writing's driving me crazy on this board. Okay, it looks like I can't write. Very frustrating. All right, so what I want to do now is talk a little bit about the graphing that's going to go on. So when you're given data that looks like this is two separate problems. When you're given data that looks like this, I want you to recognize what method you're going to use. I see a lot of students try to do method of initial rates on this, and they'll go, oh, it doubles from here to here, or triples, so that, I'm like, whoa, 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 wrong data. You don't do that on this data. How is this different than the information you were given for method of initial rates? And don't tell me there's only one reactant. You can have one reactant and still do method of initial rates. That's not it. What's different about this data compared to what you got in the other ones? Okay, they said, what if the word experiment wasn't there, though? Yeah, the other one said were experiments. That's seconds. The other one was a rate, okay? In the other set of experiments, they took a set of concentrations and found the initial rate. And then they changed it up and found the initial rate again. They changed it up. Here, someone is starting at time 0 and looking at how basically it's dropping over time. Totally different data, okay? So it's really important you recognize when to use what data. So when you see time and concentration, you're going to graph 3 ways. First, let me show you a trick of how to remember the graphing. CLR. First off, that is a cleaning product. Has any of you heard that? Calcium lime rust? No? Okay, because y'all don't clean. So that's clear. Okay, clear. It's clear how to graph this. Clear. C is concentration. L is natural log. R is reciprocal. Okay? So this is a zero order, first order, second, and all of it's versus time. So concentration, ln, reciprocal. So it's clear how to graph. Got it? All right, so our first order of business, let me tell you what to do, and then I'm going to pull up an calculator emulator here on the video so you can watch it at home as well. This is the fast way to do this. When I used to do this, I had to calculate all of the linear regression stuff by hand. I don't know if any of y'all in statistics have had to do a correlation coefficient by hand. It is a pain. I would spend close to 2 hours on each of these problems in order to figure out which one had the best fit line and graph them separately and all that crazy stuff. We didn't have the nice little graphing calculators. So the fastest way to do this is in L1, you're going to put time. Always put time in L1 because that's always going to be your X value no matter what the order is. Okay, in L2, you're going to put just plain old concentration from your list. I'm going to teach you today how to do a batch transformation, and you're going to put natural log in 3 and reciprocal of concentration in 4. Okay, once you have all that in, you're then going to do linear regression, and I'll show you how to get to that. To prove a zero order, what are we going to do linear regression of? Which two lists? L1 and L2. L1, comma, L2. To prove a first order, we're going to do linear regression on L1, comma, L3. And to prove a second order, we're going to do linear regression on L1, comma, L4. And from each of those, you're going to get all the information you need. So what I want you to do is take out your calculator. The first thing you guys need to do is turn on your diagnostics. Anytime your calculator is reset, you'll have to do this again, but we want to see the correlation coefficient. So to do that, you have to hit the second catalog feature. And do you see how alpha is up in the corner right there? It's in alpha mode. I want to hit the alpha D, which is it here, right there? It's above the x to the minus 1. And I'm going to scroll down until I get to diagnostic on. Oh, see, I have no patience with this, so I always hit it too fast. And it just goes by. I need to slow down. Hit enter once and enter again until it says done. Now you'll be able to see your R's. If at some point you can again, it's because somebody reset your memory. All right? So to get to your list, stat, enter on edit, and you have your list. To save time, I've gone ahead and entered time in L1 and concentration in L2. Everyone do that for that first problem now, and I'll pause this. Okay, now that you have that done, you are going to take your cursor to the tippy top of L3. I need to see, do you see how L3 it's blackened? We're going to do a batch transformation. What did I say we needed to put in L3? Natural log of concentration. Natural log of concentration is actually natural log of which column? L2. So to do that, once you're at the tippy top, all you have to do is hit natural log. Do you see how it's showing up underneath the list? And then second, L2. If you hit the second number 2, L2 pops up. You don't even have to close your parentheses. Hit enter, and it does it all for you. Some of you on that last lab are probably doing one at a time, 1 over t, 1 over t, 1 over t, right? You can do it all with this batch transformation here. Okay? So what did we want to put in L3? I'm going to scroll over. We wanted to put 1 over concentration, which is 1 divided by what list? L2. So 1. Make sure if you don't have the tippy top blackened and have the first space blackened, it's only going to do 1 data point. We wanted to do all the data points. So 1 divided by second number 2. Hit enter, and there are all our other L's. I mean our other concentrations in reciprocal. Is everyone good? So now, hit stat. We're going to do linear regression. Scroll over to calculate. Number 4 is linear regression. If you just hit enter here, it defaults to 1, 2. I'm just going to show you how to enter it though, because I want you to enter it for every time something. L1, comma is above the 7, L2, enter. There you go. That is what you need to write down. Instead of me hopping back and forth, I need you guys to jot this down really quick, and I'm going to pause it. So here we have a slope of -4e -8, and our r squared is 0.9944. Remember, perfect is 1. That's a pretty good line, right? But will the other ones be better? I don't know. We're going to have to see. So now we're going to go ahead. What order was this for? 0. So now let's go ahead and do linear regression for second order. Stat, calc, linear regression, but this time it's L1, comma, L3. Whoa, our r squared is 0.99989. Jot that down. Make sure you have your slope of negative 3.41e, -5. A lot of people don't see the e over here. Watch that. Okay. When you show your work, I want these regression equations down. That's the only work I expect of you, is to show me you actually did the linear regression 3 times. All right, last time. Stat, calc. Now we're going to go ahead for a second order. 4. L1, comma, what now? L4. Enter. Is that as good? No, 0.994 versus a slope of 0.0296. So jot those down. Okay, I'm going to go ahead and exit this and go back to my problem. So, which we determined this order to be? First order. Can someone tell me what the, that's the best, what the r squared was? 99989. And what the slope was? 3.4 what? Times 10 to the -5. Okay. So if I were to ask you to write the rate law, what would you do? You would go rate is equal to, yay, I got my K, 3.41 times 10 to the -5. What are the units? This is a what order? First, so it's just 1 over, how do I know it's seconds? Look at your data. 1 over seconds, okay, times N205 to what power? To the first, because it's first order. All right, on your own, go ahead before the bell rings. You've got about 7 minutes. I'm going to pause the video. I want you to do the second one on your own, and then before class is over, I'll jot up on the video on the screen what the correct answer is so people at home can practice on their own. So for this reaction, our final ended up being a second order reaction with a rate constant of 0.548, 1 over molarity times seconds, times the concentration of NO2 raised to the second. That is your rate law. The end.